Now coming to the example number 7. This is the multiplicative group of integers modulo n. That is also called the group of prime residue classes modulo n. So these two names are popular for it. Now the problem was that in Zn this was the group with respect to addition, and there was one more operation, that was the operation of multiplication, but with respect to multiplication it was not the group because there were elements whose inverse does not exist. So what we will do is that we will take all those elements of Zn which has multiplicative inverse, and that will form a group that is called the multiplicative group of integers modulo n, or group of prime residue classes modulo n. So let us introduce it. So for it, first fix n in n is a natural number, and now this group is denoted as, this set is denoted as un, and it consists of elements those a such that a and n has GCD 1 and a belongs to Zn. So you will write it as a n bar. So those a n bar in Zn such that the GCD between a and n is 1. Now, so we will show that it is a group with respect to multiplication operation. So first we have to show that if we take two elements in this set, then their product will be in this set. So suppose I take a bar b bar in un. So it means that the GCD between a and n is 1 and GCD between b and n is 1. So if the GCD between these two is 1, then the GCD between AB and n will also be 1. So now we know that what is a bar into b bar. By definition of multiplication, a bar into b bar is ab bar. But because the GCD between AB and n is 1, so it means this AB belongs to un. So this implies AB bar belongs to un. So we can define the operation of multiplication from un cross un to un, because product of two elements of un belongs to un. So now this dot is a binary operation, that is multiplication is a binary operation on un. So this is a group I. This is a group I. Now further we will show that this operation is associative. So now take three elements a, b, c in un, then clearly a bar dot b bar dot c bar. This by definition you can write it as a into b whole bar into c bar, and by definition again you can write it as ab into c whole bar. But ABC are natural numbers and the product in natural numbers are associative. So you may write it as a into bc whole bar. So you may write it as a bar bc whole bar, and you may write it as a bar b bar into c bar. So, and this is true for all ABC in un. So un with respect to this dot is a semi group. So this is a semi group. that always in UN there is an element 1 bar that will always be in UN because the GCD between 1 and n is always 1. So this 1 bar belongs to UN, so it means you take any element a bar in UN, then a bar into 1 bar will give a into 1 whole bar, that is a bar. And similarly you can write it as 1 into a bar, so that is 1 bar into a bar. So 1 bar is the identity element. So identity exists, so UN with respect to dot is actually a semi-group with identity. So this is a monad. This is a monad. Now what about the inverse? Now the main thing is that we have to show that each element has inverse. So take an element a bar in UN. So a bar is in UN. This implies that the GCD between a and n is 1. Now GCD between a and n is 1 means there exist two integers uv, that is the set of integers. So there exist two integers uv such that a into u plus v into n is 1. We can always do this. For example, let me give you an example. Suppose I have n is equal to 5 and I take a to be 2. So the GCD between 2 and 5 is 1. Then we want to find u and v. So let me divide 5 by 2. So this is 2, 2 is 4, so I am getting 1. So 1 can be written as 5 minus 2 into 2. So 1 can be written as 5 minus 2 into 2. So it means 1 can be written as 1 into 5 plus minus 2 into 2. So for this example, this 1 is v, so this is our v, n is 5, and u is minus 2, this is u, and a is 2. So this combination will always exist. Now what can we do is that, now we take bar on both sides, so we have au plus vn whole bar is equal to 1 bar. By the definition of addition, we can write it as au whole bar plus vn whole bar is equal to 1 bar, and au whole bar means a bar into u bar plus v bar into n bar is equal to 1 bar. But n bar is 0 because I am taking everything to modulo n. So n bar is 0. So 0 into v is 0, and 0 plus something is 0. So I can simply write it as this is equal to 1 bar. So it means a bar into u bar is 1, and a bar into u bar is 1 means that u bar is the inverse of a bar. So a bar inverse is u bar. Now one more thing. So inverse is u bar, but whether this inverse belongs to un or not. So now we can see from here that the GCD between a and n is 1. If there is a GCD between, so now from here let us think, GCD between a and n is 1. If B is a GCD between you can see that D will divide left hand side, that is AU plus BN. So this implies D divides 1, so this implies D has to be 1. So it means the GCD between U and N is also 1, so this implies U bar belongs to UN. So we have shown two things. One thing is that A bar inverse is U bar and that U bar belongs to UN. It means the inverse exists in UN. So we can say that inverse exists for all A bar in UN. So hence UN is a group. With respect to dot is a group. Let me give some more examples of UN. Suppose I take n is equal to, suppose I take n is equal to 7. So I am talking about U7. So how many elements does this U7 have? You can see 1 is co-prime to 2, 7, 2 is co-prime to 7, 3 is co-prime to 7, 4 is co-prime, 5 is co-prime, 6 is co-prime. Co-prime means GCD of 7 and 6 is 1, 7 and 5 is 1, and so on. So actually Z7 has 7 elements, 0, 1, 2, 3, 4, 5, 6. And out of these 7 elements, we have just 0 left, and all the other elements will come because the GCD between 7 and these elements are 1, because actually the 7 is a prime number. So that's why it is happening. So suppose I take any element here, suppose I take 5 in U7 and I am asking you, so what is the inverse of 5? So whenever I am writing 5, it means 5 bar, you can do it by yourself so long. So 5 bar I take in U7 and I want to know what is 5 bar inverse. So how will you determine? Just as we have done. So what is the inverse of 5 bar here? So we will divide 5. So we will get 2 and we will divide again. This is the method how we find the GCD. So 2 2s 4 and 1. So actually the GCD between 5 and 7 is 1, and now this 1 can be written as 5 minus 2 into 2 from here. Now further, so this is 5 plus minus 2 into 2, and this 2 can be written as, so everything we want in terms of 7 and 5, so minus 2 into, this is 7 minus 5, so we can write it as 5 plus minus 2 into 7, and this minus and minus will become plus 2 into 5, so we can write it as 3 into 5 minus plus minus 2 into 7. So this is our 1. So it means we get two integers 3 and minus 2 such that 3 times 5 plus minus 2 times 7 is 1. So if I take bar on both sides, so what will happen? If I take bar on both sides, then this is 1 bar. 1 bar is equal to 3 into 5 whole bar, 3 into 5 whole bar plus minus 2 into 7 whole bar. This is 3 bar into 5 bar plus minus 2 bar into 7 bar. But 7 bar is 0, so it means 3 bar into 5 bar is 1 bar. So what is the inverse of 5 bar? So the inverse of 5 bar is 3 bar. Now Let me explain this thing by one more example. So let me explain this thing by one more example. So suppose I take n to be 5, n to be, suppose I take 6. So if I take n to be 6, then we have Z6. Z6 has 0 bar, 1 bar, 2 bar, 3 bar, 4 bar, 5 bar, this many elements, and out of these elements we have to take those elements which are co-prime to 6. So U6 will be 0 bar will not come, 1 bar will come, 2, 3 will not come, 4 will not come, only 5 will come. So now what is the inverse of 5 bar? Here 5 bar inverse here, if we determine, then we can see that the GCD between 5 and 6 is 1, and simply 1 can be written as 6 minus 5. So now, so 1 can be written as 6 into 1, you can say, plus minus 1 into 5, like this. So we can take bar on both sides, this, like we can take bar on both sides. So now, so 6 bar is 0, so 1 bar is minus 1 bar into 5 bar. So what is the inverse of 5 bar? This is minus 1 bar. Now what is minus 1? This is the additive inverse of 1. So it is 6 minus 1. So it is again 5 bar. So inverse of 5 bar is 5 bar. So the inverse varies, as we have seen that inverse of 5 bar was 3 bar in U7, but in U6 the inverse of 5 bar is 5. Now one question you may think that how many elements, so there is a question, how many elements does UN has? So actually the answer of this question is the UN has those elements A bar in Z and such that A and N is 1, and there is a function that is called the Euler function, Euler quotient function, whose value at n is exactly the same as the cardinality of un. It tells you the number of those integers which are less than n and has GCD 1 with n. So actually the order of un will be phi n, and formula for phi n is phi of, if n is an integer, then n can be written as a product of primes. So always this n can be written as some prime p1 to the power alpha 1, another prime p2 to the power alpha 2, and suppose pr to the power alpha r. Then phi of n is equal to this p1 to the power alpha 1 minus p1 to the power alpha 1 minus 1, and similarly p2 to the power alpha 2. So let me write it as p2 to the power alpha 2 minus p2 to the power alpha 2 minus 1 up to pr to the power alpha r minus pr to the power alpha r minus 1. So you can calculate it if you want. So for example, suppose I want to determine how many elements does this U12 has. Suppose I want to determine the number of elements in U12, so this will be phi of 12, and phi of 12 can be written as phi of 2 square into 3. So by this formula, this is 2 square minus 2 into 3 to the power 1 minus 3 to the power 0, so 1 less power. So So this is 4 minus 2, so 2, and this is 3 minus 1, so 2, so there will be 4 numbers, and you can see that how many numbers are co-prime to 12 in between and less than 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So how many of them are co-prime to 12? So you may count it also. So if I want to ask, I ask you to write U12, so you can see 1 is there, 2 is not, the GCD between 2 and 12 is not 1. So 2, 3, 4 will not come, so 5 will come, 6 will not come, 7 will come, 8 will not come, 9 will not come, 10 will not come, 11 will come. So these are the 4 elements. So as we have seen that the order of U12 is 4, so you can also see here that U12 has 4 elements. Okay, so we are now going towards the next example. Example 8. Consider the set R greater than 0. What is that set? This is those real number x in R such that x is greater than 0. So clearly 0 is not here. If you take product of two positive real numbers, you will always get a positive real number. So it means we can define multiplication operation on this set, and that operation will be binary operation. So R dot, this is a group item. But you know that the multiplication of real number is always associative, so it is not only a group item but it is also a semi-group. You also know that 1 belongs to R greater than 0, and if you will multiply any real number with 1, you will get that real number itself. So this 1 will work as identity, so this set is nothing but monad. One more thing you know, that if x is a real number and positive real number, then 1 by x is also a positive real number, and x into 1 by x is always 1. So it means inverse exists. So this, you can say that R greater than 0 with respect to multiplication, this is a group. This is a group. Similarly, one can show that this Q greater than 0 with respect to dot, this is same thing, those rational numbers which are greater than 0, this is also a group. This is group. So before moving forward, let me define what is commutative group or abelian group. Abelian group. Both the terms are used, commutative group or abelian group. So a group GO is called abelian group if A of B is equal to BOA for all AB in G. So if in a group A of B and BOA are same, then that group is called abelian group. For example, if you remember, all the groups of example 1 was abelian group. because addition of real number, addition of complex number, addition of rational number or addition of integers, these all follow this rule that a plus b is equal to b plus a. All the groups of example 2 are also abelian group. In example 2 we have taken the q star with respect to multiplication, r star with respect to multiplication, c star with respect to multiplication, and multiplication of numbers is always a commutative operation or abelian operation. A into b is equal to b into a. Then in example 3 we define circle group S1, which is again with respect to the complex multiplication, and complex multiplication is commutative. So this third example, that was also an example of abelian group. Fourth example, fifth example, roots of unity and nth root of unity, both are due to the multiplication of complex number, so they are abelian operation. Sixth operation, sixth example, seventh example, and eighth example. Sixth example was integer modulo n with respect to addition. So integer modulo n operation is also abelian, because when you will take, then you will get this thing, and this is same thing as y plus x bar. So this is y bar plus x bar. So this was an abelian operation. Seventh operation, unitary group, and this was a group with respect to multiplication. So x dot y is x dot y whole bar. This is y dot x whole bar. This is y bar dot x bar. So again it is an abelian operation. And this eighth operation is the multiplication of real numbers. Eighth example is the multiplication of real number. This is also an abelian group, and similarly this is also an abelian group. So all the above examples, 8 examples which we have done up to now, is an example of abelian or commutative group. So now come to the example number 9. Example 9. This is Klein's 4 group. Klein's 4 group. It is denoted as K4 or V4. Both the notations are popular. Some books write it as K4 and some books write it as V4. So what is this group? V4 is a set actually, and in this set there are 4 elements. This E is an identity element, and there are 3 more elements. And because these are just 4 symbols, so we need to define the operation O, and that can be defined by writing all the elements in the multiplication table. So E will work here as the identity element. So when you will compose E with any element, you will get the same element. So this is E, A, B, C, and here it means E from the right side. If you will compose, then again you will get the same element. And now how ABC will be multiplied? Square of any element is means A composite with A is identity, B composed with B is identity, and C composed with C is identity. And any 2 element when you will multiply, you will get the third element. So AB is C, AC is B. So BA is A, BA is C, and BC is A, and CA is B, and CB is A. So this is the multiplication table, and you can see that this is clear that it is a binary operation, and I am leaving exercise, show that V4 with respect to this operation O is an abelian group. This with respect to this operation is an abelian group. Abelian is very easy to see. You can see these are the diagonal elements. And if it is abelian, then A composed with B should be equal to B composed with A. So B composed with A is C and A composed with B is also C. So if you will see only this part, and in case of abelian group, this matrix will be a symmetric matrix. So you can see it is a symmetric matrix ABC, ABC, AECB, AECB, BCEA, BCEA, and CBAE, then CBAE. So it is a symmetric matrix. So it is an abelian group. So it is quite easy to check the associativity. What will work as identity? E will be identity. And what are the inverses? A inverse is A, because A into E is identity. B inverse is B, and C inverse is C. So each element has inverse. And this is again an example of Klein abelian group. That is called the Klein's 4 group. Now I am coming to an example of non-abelian group. So I am giving you 9 examples of abelian groups. There are many more, but 9 examples I have given you. So now example 10. And that is Quaternion group. Quaternion group. This is usually denoted as Q8. And it has 8 elements: 1, -1, I, -I, j, -j, k, -k. These are 8 elements, and we need to define an operation on this set. So for defining the operation, we can make the whole multiplication table. So let me do it, and I will also give you the trick how to fill this multiplication table easily. So let me first make the multiplication table. So 1, -1, I, -I, j, -j, k, and -k. Similarly, we have elements here. So the operation you can denote it by dot. 1, -1, I, -I, j, -j, and k, and -k. So how to fill it? 1 will work as identity element. So product with 1 will give you the same element for any element, j, -j, and k, and -k. Similarly on this column, -1, I, -I, j, -j, k, and -k. So I write all these elements here because 1 is identity element in this group. Now, in this group, I square, -I square, j square, -j square are our same element, k square and -k square are our same and is equal to -1. So, and of course -1 square is 1. So we can put the value of squares of all the elements. So -1 into -1, 1, I into I is -1, -I into this is -1, this is minus 1, minus 1, minus 1 and minus 1. These all are minus 1. And how to multiply with I, j and k? So make a circle like this, and I, j and k you can take. So whenever you will multiply, there are 3 I, j and k. So this is I is here, j and k. So if you will go like this, then you will have positive sign, and if you will go opposite, you will have negative sign. Means if you will multiply I into j, you will get k, but if you will multiply j into I, then you will get minus k. So if you will multiply j into k, you will get I. If you will multiply k into j, you will get minus I, and so on. So go like this, multiply any two, you will get the next one. So if you will go like this, multiply any two, you will get minus of next one. Okay, so let us do it. And another thing is minus 1 into anything. Minus 1 into I is minus I, and similarly minus 1 of j is minus j, and minus 1 of k is minus k. So minus 1, when we will multiply, the sign will get changed. So minus 1, this is minus I, minus j, minus k and k. And similarly when you will multiply minus 1 here, so this is minus I, this is minus j, this is j, this is minus k, and this is k. So like this. Now again I and minus I you want to multiply. So I and minus I means minus times I into I, that is minus of minus 1, so it is plus 1. So I into minus I is plus 1, minus I into I is plus 1. Similarly j into minus j is plus 1, and minus j into j is plus 1. Similarly k into minus k is plus 1, and minus k into k is plus 1. Now let me multiply I with j. So I into j, we will get k. I into minus j, if you will 2. So I into minus j simply means minus of I into j, and I into j is k, so you will get minus k. So I into minus j is minus k. Now I into k, we are going like this, so it is minus j, and I into minus k, if we multiply, we will get j. So like this, let me put here. So when you will multiply I, you are getting this thing. When you will multiply minus I, you will get negative of this thing. So you are minus k, j and minus j. Now multiply with j. So j into I is minus k, and this is k, and then j into k is I, then it is minus I. Similarly minus j, when you will take, so you will get just opposite sign. K means minus k, and this is minus I, and this is I. You will get negative sign. And when you will multiply k, then k into I, you have to go opposite in this way. So you will get j, and then when minus I, then it is minus j. So k into j, you have to go like this. So minus I, and k into minus j means I, and now minus k into I. So k into I is j, so you are getting minus j, and then this is minus I, so it is j, and minus k into j, so k into j is I, k into j is minus I, so you will get I here, and k into minus j is minus I here. You can see one thing, in each row and each column there will not be any repeating in this matrix. Each entry will be unique 1 minus 1 I minus I j minus j k minus k, 1 minus 1 minus I j minus k minus k. There will not be any repetition. There will not be any repetition. If there is any repetition, then you have made a mistake, which we have not done till now. So yes, we are right. So this is the multiplication table for Q8. So we can multiply any two elements of Q8, and now I am leaving it as exercise to show that Q8 with respect to this multiplication is a group. This operation is actually associative, you can check it, and one will work as an arity element, and inverse of minus 1 is minus 1 because minus 1 into minus 1 is 1. Inverse of I is minus I because this is giving you 1. Inverse of minus j is minus I is I. Inverse of j is minus j, you can see. And similarly inverse of minus j is j. Inverse of k is minus k because you are getting 1. And inverse of minus k is k. So each element has inverse, and of course identity is into identity is 1. So this is a group. And one more thing you can see, that this matrix is not symmetric. So it is not an abelian group because I to j is k, but if you will multiply j into I, you will get minus k. So this is non-abelian group. This is an example of a non-abelian group.